Today's video is about gas power cycles. Now, back in the entropy video, we introduced the concept of an ideal reversible cycle, and we mentioned that the Carnot cycle is the most famous form of a reversible cycle. Now, just to refresh your memory, this graph here represents the TS diagram for a Carnot cycle. We have a heat addition process from 1 to 2. We have a work or power producing expansion from 2 to 3, a heat rejection from 3 to 4, and of course, a power consuming compression from 4 to 1. Now, the thing is, this diagram represents an ideal Carnot cycle. But the issue is that the Carnot cycle, while being very useful for understanding the physics behind a power cycle, is not really practical. To understand that, let's focus on the heat addition process. If you review the introduction to Carnot cycle, you will see that for the heat addition to be a completely reversible process, we had to have the heat addition over an infinitesimal temperature difference between the system and the surroundings. That way, we could ensure that the process from 1 to 2 is truly reversible. However, in practice, that is not achievable. From a heat transfer perspective, the higher the temperature difference between the source and the system is, the better the heat transfer rate will be. So a delta T of approximately 0 is not practical. Also, if you look at the power producing expansion, you will see that in order for this power expansion to be truly reversible, we had to have the expansion at a super slow rate to ensure that the system and its surroundings will remain reversible. So Carnot cycle, very good for understanding the physics, not very practical in real life applications. So we have to look for and settle for the next best thing. We usually call them the ideal cycles. Now, as the name suggests, these are still ideal and theoretical. They are far away from what happens in practice within a system, but they are a good approximation nonetheless. We can use some of the basic understandings of the thermodynamics that we have gathered so far and understand what is happening in a practical sense. So what makes the ideal cycle different from a Carnot cycle? For starters, we do not care for the processes to be truly reversible. We want them to be internally reversible. An internally reversible process means that we do care for the system to go back to its initial state if we reverse the process, but we do not care about the surroundings. So, for example, when we are adding heat, we want to make sure that the system can lose the same amount of heat and go back to its initial state, but we don't care what happens in the surroundings. So that is the main difference between an ideal cycle and a Carnot cycle. These cycles are not reversible, they are internally reversible. So although the ideal cycle is now internally reversible, it is still an ideal cycle, meaning that we don't want to deal with any friction in the system, which means no pressure drop in the system. And also, we don't want to deal with any unwanted heat transfer between the system and the surroundings. So no heat loss. And I want to emphasize unwanted heat loss. We are going to discuss gas cycles, ideal gas cycles in this video, but even if you are dealing with ideal refrigeration cycles or ideal vapor power cycles, these three conditions are the same for any ideal cycle. It is internally reversible, there is no friction or pressure drop, and there is no unwanted heat transfer with the surroundings. Now, focusing on the gas power cycles, we have to make a few assumptions regarding our working fluid, which is air. So the conditions that we are going to assume are very straightforward. Number one is that air is an ideal gas. Throughout the cycle, regardless of what process it goes through, we are going to assume that air is an ideal gas. The second assumption that we make is that air does not leave the system or enter the system. Air is trapped in a closed loop. More on this later when I'm going to show you how a typical cycle works. I'm going to explain why this is kind of true from a theoretical perspective and how it helps us analyze the cycles more efficiently. The next assumption that we are going to make is that the air composition through the processes is going to remain the same, meaning that combustion, which we know in practice changes the composition of air, uh, is not affecting air properties from a thermodynamic perspective. So, no chemical reactions. And finally, we are going to assume that the combustion, which is the source of energy in a power cycle, can be replaced by a heat addition process. And the exhaust process, where we, push the combustion products out of the engine, can be replaced by a heat rejection process. So internal combustion engines usually fall into two categories: spark ignition and compression ignition. Now, the spark ignition engines are the ones that you see in your car. They usually run on gasoline or just gas, as it is sometimes referred to. Compression ignition engines are the ones that we usually have in more heavy duty situations like the ship propulsion or a tractor, a heavy machinery, and they are usually running on diesel fuel. You can have cars that are running on diesel fuel as well, which have the compression ignition, but most of the market is, at least for commercial cars, is dominated by the gasoline engines, which are spark ignition. Now, what is the difference between these two? Before we go ahead with the cycles, it may be beneficial to discuss the differences. The difference is very, very simple. An spark ignition engine relies on a external spark, if you will, to start the combustion process. You may know that the cylinder in your car's engine has a component called spark, which relies on electricity to create a electrical arc that starts the ignition of the gasoline inside your cylinder. So that's very easy to understand. Compression ignition, on the other hand, relies on the fact that some chemical components, when they reach a certain pressure or temperature, will start to ignite, will start the ignition process automatically. That's how the compression engines work. They rely on the high temperature and high pressure of the gas mixture to start combusting on its own and not rely on an external source like a spark to start the process. Okay, with that said, let's start talking about spark ignition. engines. The cycle that governs the spark ignition engine is called the Otto cycle. Now, here I want to emphasize that in this video, we are going to focus on a four-stroke engine and not a two-stroke engine. The principles are the same, so probably you can uh, do an analysis if you really want to on your own. But because the two-stroke engines are of limited use, we are going to analyze the four-stroke ones, which are the most common form of spark ignition engines. Now, before we can start talking about the actual process, we need to gather a bunch of information about uh, an internal combustion engine. Mainly, we need to gather some information on the cylinder and the piston. So, let's start. A typical piston and cylinder setup in an internal combustion engine looks roughly like this. Say this is the cylinder, and this here is the piston. We have the intake valve and the exhaust valve on top of the cylinder, like so. So this one is the intake valve, and this one is the exhaust valve. Now, the diameter of the cylinder usually is referred to as the bore of the cylinder. And there is a limit to the range of motion of the piston. What I mean by that is this piston can move up all the way to maybe this point. It will not go all the way to hit the intake and exhaust valves. It can only move up all the way to the pink line. Now, the pink line is referred to as top dead center. We show it with TDC. And the volume above the TDC, the volume that the piston cannot touch, is sometimes referred to as the clearance volume. So that much is clear, nothing too crazy. We have the same limit on the bottom of the cylinder. The piston can only travel so much down inside the cylinder. Let's say that's the pink line again on the bottom. We call this the bottom dead center. And we show it with BDC. Now, the length of a single stroke of the piston is the distance between the two dead centers. And the volume between the TDC and the BDC is referred to as displacement volume. So when you check your car's engine and it says, for example, a 2.4 liters or something like that as the capacity for the engine, it is referring to the displacement volume of each of the cylinders in your engine. Your car engine typically has something between 4 to 8 cylinders, depending on the model, make, and how loud you want the engine to be. Okay, so based on this little drawing here, we can introduce a very important physical property of a internal combustion engine. We show it with R, and it is the ratio of the maximum volume to the minimum volume within our system. Now, if we look at the drawing, the maximum volume for our system is the volume of the system when the piston is at the very bottom. So one can make the argument that this is the volume of the bottom dead center. With the same logic, you can see that the minimum volume for your system is when the piston is on the very top, which is the top dead center, and you can say the V minimum is TDC, or also the clearance volume. They would be the same thing. We refer to this property as compression ratio. This is very important, and we are going to see it later within the equations that we are going to drive for the Otto cycle. Okay, now let's see if we can develop an idea of how a four-stroke engine actually works. Overall, there are different ways of looking at the sequence of a four-stroke engine. For me personally, I like to start from where the fresh mix of air and fuel enters the cylinder. So we are looking at a scenario where the piston is at the top of the cylinder. Here, and it is going down. Now, please keep in mind that this is the top dead center. So while the piston moves down, the volume in the piston expands and a fresh mix of air and fuel enters the cylinder. Now, please take note that this expansion of the piston down and entrance of the fuel into the system makes the system experience a constant pressure expansion. So this can be approximated by a constant pressure process. I would like to show this process on a diagram with 0 to 1 notation. I'm going to keep track of what is going on this PV diagram. I said this is P and this is volume. Now, the thing about the mixture of air and fuel is that typically you're looking at an air mixture that has entered the engine from the grill in front of the car, and usually you're looking at the air at atmospheric pressure. So I'm going to say that process 0 to 1 looks like this, kinda. Keep in mind, we are looking at the practical problem right now. So this is 0 to 1. A few things that are worth mentioning is that, remember, the process starts where the piston is at the TDC, at the minimum volume. So this is V minimum. And the process ends when the piston reaches the BDC, the maximum volume. So right away, you can see that the maximum volume in our system is equal to the volume of state 1. Now keep that in mind, and we are going to continue. So the next process begins right after when the piston hits the BDC, the piston starts to go up again. It will be the second stroke, right? The piston starts to move up, during which both the intake and exhaust valves are closed, and this air mixture is going to get compressed. So the second process, the piston was all the way down. Now it's moving up. from the bottom dead center. Now, both intake and exhaust valves are closed, so we are going to experience compression. So this compression looks like something like this. Again, remember, we are looking at the actual practical cycle, not the ideal one. So from 1 to 2, I expect a compression that looks like this. So putting it on the paper, this stroke is compression. And I would like to show this stroke with 1 to 2. And that's where you get 1 to 2. Now, please keep in mind that the piston, while going through the compression, can only reach to the TDC, right? So the volume of the system at state 2 is equal to the minimum volume, which instantly tells me that the minimum volume of the system is equal to volume 2. The moment the piston reaches the top dead center, something very interesting happens. The moment that the gas is compressed to its fullest, the spark ignites the mixture. Now, this combustion, so this is the spark, it happens so fast that the piston has not yet got the chance to move down when the burning process is happening. So this burning process or combustion process is the process that, with our assumptions, we mentioned we are not going to go through the chemical reaction, but we are going to model it as a heat addition, right? So first of all, I would like to show this heat addition process with 2 to 3 notation. So now I can show this combustion with a process 2 to 3 like this. Keep in mind that the piston has not yet have chance to start moving downwards, so the whole heat addition part or the combustion part happens at the constant volume from 2 to 3. Next on the stroke list, the hot gas here, because of the combustion, is now experiencing high pressure. You can even see that here when we added heat or the combustion process from 2 to 3 while the piston was on top at the TDC, the pressure of the gas spiked high, right? So this high pressure gas is now pushing the piston down. So for our next stroke, we have a scenario where the piston is moving downwards due to the push by the high pressure gas. In other words, this is an expansion. So the third stroke is the expansion due to combustion. I would like to show this with 3 to 4 notation on the PV diagram. So from 3 to 4, you're expecting to see something that looks like this. Now, please keep in mind that this piston can move to a certain range. It can only move all the way to bottom dead center. And as we discussed in the first stroke, we know that the bottom dead center is volume 1. So you can kind of see that volume 4 is equal to volume 1 because it's the bottom dead center. Now, finally, for the last stroke, we have the piston moving up again due to the rotation of the crankshaft. This time, when the piston is moving up, it is pushing out the burnt mixture of air and fuel through the exhaust valve. Because the piston is moving up and the gas is moving gradually out of the system, we can kind of assume that the pressure within the system remains constant. So this is the fourth stroke. And I would like to show it with process 4 to 0. As I said, the pressure remains constant for this process where the burnt air and gas mixture is leaving the system. So now you have all 4 strokes of an engine. The next stroke, now that the piston is on the top dead center, the next stroke is the first one that we had here. The piston starts to go down, mixed air and fuel will enter, and the cycle starts again. So these are the 4 strokes, and this diagram here is the practical or real cycle that the air goes through. Now, through the analysis of 4 strokes of an internal combustion engine, we were able to come up with the real cycle PV diagram. But we are far from an ideal cycle here. First of all, if you review the assumptions, we want to treat air as a working fluid that is trapped within the system. From a practical, real point of view, the air that enters your engine and goes through the 4 strokes leaves through the exhaust and goes out of your car, right? That is the process from 4 to 0. However, from a thermodynamic analysis perspective, we really don't want to lose that air out. So let's take a closer look at processes 0 to 1 and process 4 to 0. One can make the argument that 0 to 1 and 4 to 0 are very, very close to each other in opposite directions. So if, for example, you are analyzing this from a work perspective, 0 to 1 is an expansion. So you are getting some work out of this expansion. Whatever the work is, that will be equal to the area of the pink shaded rectangle. From 4 to 0 perspective, you are looking at a compression. So from 4 to 0, you are applying work to your system to compress the air out of the cylinder. And that amount of work is the orange rectangle. So you can see that the orange and the pink rectangles are kind of the same, indicating that whatever work you are getting from 0 to 1 is equal to whatever work you are losing from 4 to 0. Now, if we focus on the heat addition part, 2 to 3, you can clearly see that this heat addition is a constant volume process. If you track the volumes down, you see that the entire combustion happens when the piston is at TDC, which is the minimum volume of our system, as you can see down here. And so 2 to 3 is a constant volume process. Now that we know 4 to 0 and 0 to 1 are kind of the same processes, we can look at 4 to 1. Yes, in a real cycle, they are not connected. But when you look at 4 and 1, you realize that they are sharing the same volumes at states 1 and 4. And 4 to 0 and 0 to 1 are the same. So it kind of makes sense to treat this portion of the cycle as the heat rejection part and replace it by a constant volume process. If we do that, then we can come up with the PV diagram of an ideal Otto cycle. So let me draw it down here for you. So this is P, this is volume, 0 to 1, 1 to 2, 2 to 3, 3 to 4, and 4 to 1. Putting the small arrows just to show where the cycle moves, 0 to 1 and 1 to 0. So this is the ideal Otto cycle. In this ideal form, 0 to 1 and 1 to 0 are constant pressures. 1 to 2 is an isentropic compression. 2 to 3 is a constant volume heat addition. 3 to 4 is an isentropic expansion. And 4 to 1 is a constant volume heat rejection. Okay, so why we are saying isentropic compression and isentropic expansion? We did not cover that in the practical real cycle. For understanding these two processes, the isentropic compression and isentropic expansion, we need to go back to the assumptions that we made at the beginning of the video. We said that we want to deal with an ideal cycle. This ideal cycle was internally reversible and free of any friction, unwanted pressure drop, and unwanted heat transfer. Now look at the process 1 to 2. If 1 to 2 is frictionless and also is not experiencing any unwanted heat transfer, in other words, is adiabatic, then it is isentropic. Right? That's what it is. This is an isentropic process. The same goes for 3 to 4. It is frictionless, and it does not have any unwanted heat transfer, meaning that it is also adiabatic, and so it is also isentropic. So for an ideal cycle, Otto cycle, we are dealing with two isentropic processes and two constant volume processes. Again, as you can see, let me scroll up a little bit. As you can see, the ideal and the real, they are not 100% match, but the ideal through these assumptions that we made is a good approximation of what is actually happening within the real cycle. Now, based on the orange and pink argument that I had for the work done and the work required for processes 0 to 1 and 1 to 0, we can see that this line on the PV diagram is not that important, and in most references and in most applications, like 99% of all the applications, this line is not even shown. This 1 to 2, 2 to 3, 3 to 4, and 4 to 1 is the ideal Otto cycle. We can add the TS diagram to this analysis as well. So let's say this is T and this is S. The processes are very simple. 1 to 2 is a isentropic expansion, so S is not changing. 2 to 3 is a heat addition at constant volume, so you're looking at something like this. 3 to 4 is again an isentropic expansion, so S does not change. And 4 to 1 is a constant volume heat rejection. So please take note that in this diagram, S1 and S2 are the same, S3 and S4 are the same. On the previous diagram also, please take note that V1 and V4 are the same, whereas volume 2 and volume 3 are the same. All right, so 2 to 3 is the heat addition. Or with the thermodynamic notation that we have, this is where Q in happens. 4 to 1 is heat rejection. Or with thermodynamic notation, this is Q out. So if I want to calculate the thermal efficiency of an Otto cycle, I can frame it like this: 1 minus Q out over Q in. For each of the processes, on this diagram, we know that the first law of thermodynamics holds true. So Q in minus Q out plus work in minus work out is the change of internal energy. You might have noticed that I'm using small letter notation, Q's, works, and U, because if this is a closed system, which we know it is based on our assumptions, the mass in the system is the same. There is no mass entering or leaving the theoretical cycle. So I can divide everything by the mass of the system and work with the per mass intensive units. Okay, so with that out of the way, let's focus on what you want to do. I want to calculate the thermal efficiency of this cycle, and for each process, the first law of thermodynamics is true. From the thermal efficiency equation, I can say this is actually Q from process 4 to 1 over the Q for process 2 to 3. So these are the two processes that I need to focus on, starting with the process 2 to 3. So this is a constant volume process. So because the volume is constant, the boundary work is non-existent, right? We know that there are no other forms of work available here. There is no electricity, there is no shaft moving, nothing except the boundary work. So there is no work in and out for the process 2 to 3. Therefore, the first law of thermodynamics says that the Q in for the process 2 to 3 is internal energy at point 3 minus internal energy at point 2. Now, for an ideal gas, we know that the change in internal energy can be approximated by CV T3 minus T2. So I have the Q in the process 2 to 3. Now let's focus on the process 4 to 1. This is again a constant volume process, meaning again there is no boundary work available. Again, the Q based on the first law of thermodynamics that I've written up above, the Q from 4 to 1 is going to be simply U4 minus U1. For an ideal gas again, the change of internal energy can be approximated by CV T4 minus T1. So now I have the Q from 4 to 1 as well. Let's set this up here again. So the thermal efficiency of an Otto cycle is 1 minus Q out over Q in, which is 1 minus CV T4 minus T1 over CV T3 minus T2. CV's cancel each other, and you end up with 1 minus T4 minus T1 over T3 minus T2. Okay, so let's keep it here for the time being. And let's now focus on the other two processes that we kind of neglected. Processes 1 to 2 and 3 to 4. Starting with 1 to 2, it is an isentropic process. We know that for an isentropic process, T1 over T2 is equal to volume 2 over volume 1 raised to K minus 1, K being the ratio of specific heats. For the other process, process 3 to 4, we have again an isentropic expansion, right? So on this isentropic expansion, again, one can use the isentropic equations for an ideal gas. T4 over T3 is V3 over V4 raised to K minus 1, K being the same thing, Cp over Cv, specific heat ratio. Now, please take note that because 2 to 3 is a constant volume process, V2 is equal to V3, and because 4 to 1 is constant volume, V4 is equal to V1. This means V2 over V1 is equal to V3 over V4. Now, taking this into account and looking at the pink equations, one can easily see that T1 over T2 is equal to T4 minus T3. Okay, so this is very neat, but why do we need this? The reason is I can use this pink equation to simplify the efficiency equation for the Otto cycle. Look at this. If I play with this equation a little bit, if I factor out a T1 from the numerator and a T2 from the denominator, I get T4 over T1 minus 1 in the numerator, and I get T3 over T2 minus 1 in the denominator. Now, if you look at the pink equation, you will realize that the expression in the parentheses in the equation on top, they are the same. And so they cancel, and you get 1 minus T1 over T2. This is a very, very good equation, but we can improve it even further. Remembering that T1 over T2 is V2 over V1 raised to K minus 1, and remembering that V1 is Vmax and V2 is Vmin. You can check the graph a few pages above. You will see that V1 is Vmax and V2 is Vmin. one can say this is actually 1 minus V min over V max raised to K minus 1. Now let's continue with this down here. So I have the thermal efficiency of the Otto cycle is 1 minus V minimum over V maximum raised to K minus 1. Remembering that the compression ratio is defined as V max over V min, and combining everything together, we get the thermal efficiency for the Otto cycle is 1 minus 1 over compression ratio raised to K minus 1. As you can see, the efficiency of Otto cycle is dependent on the compression factor, R, and the specific heat ratio, Cp over Cv. If we draw the efficiency for a constant K as a function of R, we get a graph that looks similar to this. So this is the efficiency, and this is R. You can see that by increasing R, you get a very steep increase in efficiency, but after a while, the increase in efficiency kind of dies out. Now, typically, the modern age engines are designed with an R in the range of 8 to about 11. So by looking at this equation and this graph, one would wonder why not increase R as much as we can? Because when we increase R, the efficiency also increases. This is true if you look at this equation and this graph only. But in practice, increasing R means that the pressure inside the mixture also increases. Now, gasoline and air mixture is prone to self-ignite at high temperatures and pressures, meaning that even before the spark actually ignites the mixture, the combustion starts to happen out of sync. This is a phenomenon that is sometimes referred to as an engine knock. You might have heard of it. An engine knock is when a premature combustion happens within the cylinder. Because it is out of sync with the rest of the components in the engine, specifically the crankshaft, it causes tear and wear on the crankshaft, and it wears down the engine quite rapidly. So engine knock is something that we want to avoid. In order to avoid it, we have to keep R, the compression ratio, at a reasonable range. That reasonable range for the modern fuel that we have access to is about 8 to 11. So this is the ideal cycle for a gasoline engine. I'm going to solve problems from this topic in a separate video, so stay tuned for a separate upload with the problems of this topic. Overall, the analysis of these power cycles is very, very simple. All you need to know is remembering that the working fluid is an ideal gas, and also be very comfortable with how the processes are. Two of them are isentropic, two of them are constant volume. That is all you need to know to tackle problems from this topic. Now, before we end the video, there is one more cycle that we want to cover, and that is the diesel cycle. So let's start with that. Now, the good thing is that we don't need to go through the details of every stroke again, because it is pretty similar to the Otto cycle. There is a little bit of difference in a sense that we do not compress the mixture of air and fuel in the first stroke. In the first and second strokes, we only compress pure air. The reason is, unlike the Otto cycle, we are not relying on a spark anymore. So there is no spark. We are relying on the ability of air and fuel mixture to start the ignition automatically at high temperatures and pressures. We are going to rely on that. Now, this compressed air is experiencing high pressure and high temperature. Now, at this moment, when the piston is at the TDC, top dead center, we inject the fuel into this high P, high temperature air. The moment you do that, because of the high pressure, the fuel starts to combust. Now, when this combustion happens, the piston has already started to move down. Remember, there is no spark and there is no instantaneous combustion. This is a continuous process. The piston has already started to move down when the process of burning starts. So that is the difference between the diesel and the Otto cycle. And you can easily show it on a PV diagram. Let me show it to you. So again, let's say this is P and this is V, and we are looking at the cycle. The first stroke, the compression is kind of the same. You start from point 1 and you go to point 2 from the bottom dead center all the way to the top dead center. Then when the pressure and temperature are high, you inject the fuel in. As I said, the piston has already started to move down while the combustion starts to happen. So for a brief moment in the combustion process, it is as if the process is constant pressure. When that is done, when the heat addition is done, the rest of the expansion happens just like the Otto cycle, an isentropic expansion, and we reach point 4, and after that is just a constant volume heat rejection, or as we know from practice, this is when the exhaust leaves the cylinder. So the only difference between an Otto and a diesel cycle is that process 2 to 3, which is the heat addition process, is now constant pressure. So let's write down the processes here on paper. So 1 to 2 is an isentropic compression. 2 to 3 is a constant pressure heat addition. 3 to 4 isentropic expansion. And 4 to 1 constant volume heat rejection. See, the only thing that is different is process 2 to 3. This is where Q in happens, and this is where Q out happens for our cycle. I'm going to show the TS diagram here as well before we start dealing with the equations. So the TS diagram, again, is very, very similar to the Otto cycle. We start from 1 to 2, an isentropic process. So keep in mind S1 is equal to S2. Then we have a constant pressure process from 2 to 3. Then we have a isentropic expansion 3 to 4. And then we have a constant volume heat rejection 4 to 1. So keep in mind that S3 is equal to S4. Putting the arrows so that we know where the cycle moves. Okay, so next thing that we want to do is coming up with an equation for the efficiency of a diesel engine. Again, we can define it as 1 minus Q out over Q in. The only difference, again, I want to emphasize this because it is important and is really the only difference between diesel and Otto, is that Q in now is a constant pressure. Again, for every process, the first law of thermodynamics holds true. So that means for every process, Q net minus W net is equal to the change of internal energy. With that in mind, let's now talk about process 2 to 3. So for process 2 to 3, I know that, hey, Q is coming into the system, but this time, this is a constant pressure process. So I have boundary work in the form of P V2 minus V3. And this is equal to U3 minus U2. Now, please take into account that the P here is P2, which is equal to P3. Keep in mind, this is a constant pressure process. So now, if you move things around in this equation, you get that Q in is U3 plus P3 V3 minus U2 plus P2 V2, right? From before, we know that this is the definition of enthalpy. So that is H3, and this is H2. And so one can conclude that Q in for the diesel is H3 minus H2. For an ideal gas, this is perfect. For an ideal gas, we can approximate the change of enthalpy by Cp T3 minus T2. Very, very good. So I got Q in and Q out, the process 4 to 1. It is exactly like the Otto cycle. Exactly like the Otto cycle, which means Q out is this time CV. Please take note. This is now CV because it's constant volume. CV T4 minus T1. I can plug them back here. So the thermal efficiency for the diesel engine is 1 minus T4 minus T1 over Cp T3 minus T2. Now, I'm not going to redo all of the calculations that we did for the Otto cycle because you already know how to do it. Keep in mind that Cp over Cv, we show it with K, a specific heat ratio. Keep in mind that for the isentropic processes, such as 1 to 2, T1 over T2 is V1 over V2 raised to K minus 1. Keep in mind that that equation is true. And also introducing a new property calling the cutoff ratio. We show it with RC as V3 over V2. Combining everything that you see here and more, everything that we did in the Otto cycle, factoring out the temperature, relating the temperatures together through the isentropic relations, one can finally get the equation for the thermal efficiency of the diesel engine. It is 1 minus 1 over R raised to K minus 1, so far exactly like the Otto cycle, times, this is where the difference comes in, RC raised to K minus 1 over K RC minus 1. Very interesting equation in the sense that it is very, very similar to the Otto efficiency. However, it has an additional term. Let's take a look into that. I'm going to compare them here on this page. So for Otto, efficiency is 1 minus R over R raised to K minus 1. For diesel, it is 1 minus 1 over R raised to K minus 1 times something. Now, this additional expression is very interesting in a sense that if you pay attention to how we defined cutoff ratio, and if you take a look at the PV diagram, you see that V3 is always greater than V2, meaning that RC is always greater than 1. It is a positive quantity. So RC raised to an exponent minus 1 over RC minus 1 is always a positive quantity. So if that is true for same R, efficiency of the Otto cycle is greater than the efficiency of diesel. And that is true. If the compression ratio for both of your engines are the same, then your gasoline run engine has higher efficiency. However, please remember that for the diesel engine, we actually want to go to higher compression ratios because we want the mixture to ignite on its own. We don't want a spark there. So the R's that are typically used for a diesel engine can be as high as something like 24, meaning that because the R's of the diesel are so high, generally speaking, the diesel engines have higher efficiency compared to Otto engines. Because the higher R is achievable in these engines, we can use lower grade fuels that are not as refined as gasoline in these engines. As a result, the price for the fuel is going to be much, much lower. All right, so this is the end of the diesel cycle. As you saw, it is not a very complicated discussion. It is a very, very similar to the Otto cycle. It just swaps one process out for a constant pressure one, and that affects the efficiency equation just a little bit. I am going to solve problems from the diesel cycle as well in the separate video. So stay tuned for the next video, which is going to be problem solvings from Otto and diesel cycles. Thank you for watching this video, and I will see all of you in the next video.